Hello, my name is Juliana Giles. Today is May 10th, 2021, and I will be presenting my final project for this semester's Advanced GIS course at Columbus State University. The title of my presentation is Using Object-Based Image Analysis for Land Cover Classification. Object-based image analysis is an image analysis classification method that is based on image objects or groups of pixels as opposed to individual pixels like more traditional classification methods, including unsupervised and supervised classification. Object-based image analysis can be divided very roughly into two general steps. The first step is to segment the image into similar regions. Those regions are treated as objects, and they consist of pixels that have similar spectral values. And then once the image is segmented, it can be classified using traditional training sample techniques that are used in other classification methods, like the more traditional supervised and unsupervised techniques. Also, this was my first time performing object-based image analysis, and so I included a picture on this slide to kind of visualize how I felt throughout the entirety of this process. So I set out to achieve a couple of goals with this project, the first being to use object-based image analysis in ArcGIS Pro to classify land cover for 4 watersheds in Marion County, Georgia. I was unfamiliar with ArcGIS Pro at the beginning of this school semester, so I wanted to learn how to use tools in ArcGIS Pro that I might have previously known how to use in ArcMap, or to learn how to use new tools that I had not been introduced to yet. I also wanted to perform an accuracy assessment to determine the accuracy of object-based image analysis for image classification. The first question I set out to answer is, what is the percentage of each land cover type within each of the watersheds that I used for this project, and how accurate is object-based image analysis for classifying the land cover of these particular watersheds? I hypothesized that all 4 watersheds would contain mostly forest, or more than 50% of the watersheds would be characterized by forest, with lesser amounts of water, development, and barren land, and grassland and pasture. I also hypothesized that the accuracy of my methods would be acceptable so that I could use these classified land cover rasters at the end of my analysis in the future. I specifically hypothesized that I would produce accuracy greater than 90%, which is a pretty steep goal. The first thing I had to do was access some imagery of these watersheds. I was able to access some NAPE imagery through the USGS using their image server. I had to download the entire contiguous United States NAPE imagery as a layer file from this website. Once I was able to download the NAPE imagery for the entire United States, I could upload it into ArcGIS Pro, and this is what it looked like. But I didn't need the entire United States. I only needed the area that was included in the 4 watersheds that I was interested in classifying. In order to obtain the area within the USGS NAPE imagery that I uploaded into ArcGIS Pro, I needed some shapefiles of the 4 particular watersheds within Marion County that I was interested in analyzing. So I used another USGS tool was used, this time StreamStats, to locate and delineate the 4 watersheds for my analysis. This was graciously done for me by my advisor and professor, Dr. Troy Keller, and he shared the delineated watersheds with me as shapefiles so that they could be used in ArcGIS Pro. Once I obtained the watershed shapefiles from my professor, I was able to add them into ArcGIS Pro along with the USGS NAPE imagery for the United States. I think it's important to note that there are 2 watersheds for 2 different sites in Marion County. These 2 creeks, Little Pine Knot Creek and Juniper Creek, are streams that were partially restored by the Nature Conservancy in conjunction with my institution, Columbus State University. The watersheds in black at both creeks are reference locations, or they're watersheds that contain reference locations, reference stream reaches for the stream restoration that was conducted, and the watersheds in red, which Little Pine Knot Creek, you can't see the rest of the outline, but it is contained within the reference watershed as well. You can see a little bit right here. The two red watershed polygons are the restoration sites or watersheds that were impacted by stream restoration activities that were conducted. So the USGS NAEP imagery for the entire United States came in projected using the WGS 1984 Web Mercator Auxiliary Sphere projection, and the watershed polygons from the USGS StreamStats application came in unprojected. So I used the project tool for all 4 watersheds, and I projected them into the same coordinate system used by the USGS NAEP imagery. And in order to do the land cover classification at the same time for all 4 watersheds, I created a feature class for the watersheds within my project geodatabase. I used all 4 of the watersheds as a template data set when I created this feature class. Once I had the feature class created, I added 3 of the watershed polygons into the feature class that I named watersheds. The reason why there are 3 polygons in this feature class is because, like I mentioned earlier, the Little Pine Knot restored watershed polygon contains the reference polygon, so all of the area that would have been contained in that polygon is included here. And just to keep things straight visually, I only classified one of the Little Pine Knot watershed since it contained the area of both. So once I had all of the watershed polygons on the imagery, I really wanted to clip that imagery because the USGS NAEP layer file was enormous, and I only needed a very small portion of it. So I used the clip raster tool in ArcGIS Pro to clip the NAEP imagery down to the watersheds feature class that I had just created. And I used those features for clipping geometry. Once I ran the tool, this is my output. I'm sorry it's a little small. I wanted to include both of them on the slide. So for Juniper Creek, you can see that it clipped the NAEP imagery to both of the Juniper Creek watershed polygons. And for Little Pine Knot Creek, it included the imagery that would have been contained or is contained by both polygons. But remember, I just clipped it to one polygon, which was the one that included the area of both. The next step in this process was to use the Training Samples Manager in the image classification toolbox to train some samples to be used in my classification methods. I originally decided to go with these 4 land classes right here, which include water, forest, developed and barren land, and grass and pasture. But after completing this classification a few times through, I found that the shadows in the USGS NAEP imagery were really impacting my results. So I did eventually decide to create this 5th land class or land cover classification, which included pixels that I considered to be shadows. I also ran into a little bit of a problem in terms of not having enough samples for each of my classes within the training sample schema. So I made sure to get a sufficient number of samples. I tried to stay between 90 and like 170 samples per land cover class. The next step was to start the image classification wizard, which is a function within ArcGIS Pro. I chose a supervised classification method and an object-based classification type. I uploaded the classification schema that I created in the Training Samples Manager, and I also uploaded or included the training samples that I had traced on the image prior to this. After I had the image classification wizard configured, I moved on to segmentation. Increasing the spectral detail increases the number of segments that are created by the tool, and so I chose to go with a value of 12 here, just because I didn't want to create more segments based off of super subtle differences in spectral signatures. I read that a decreased spatial detail results in a smaller spatial output, so I decided to go with a value of 10, which is in the middle as well. Decided that would be best for the image that I use based off of what I read in ArcGIS Pro. And then for the minimum segment size in pixels, I went with a value of 20. I think the maximum is 256, but I read that the minimum segment size in pixels should be set higher for higher resolution data sets, and I didn't feel that the data set I had was high resolution enough for me to have a large minimum segment size. After the setting up the image segmentation pane, these were my outputs. So this is the segmented image for Juniper Creek for both watersheds. And this is the segmented image for Little Pine Knot Creek for the area of both watersheds. The next step in the image classification wizard is the train panel. For my analysis, I chose to use a support vector machine as the classifier because I read in ArcGIS Pro help that support vector machine is less susceptible to noise. It can work with segmented images. It's less susceptible to error caused by correlated bands, and also like an uneven number of training sites within each class. And so I decided it was important for me to use that classifier. I left the maximum number of samples per class at the default, and left the segment attributes at the default as well. Once I had the classifier trained, I was able to run the classify tool. I just named the output classified dataset, and this is what I generated. So this is the classified dataset for Juniper Creek, and this is the classified dataset for Little Pine Knot Creek. Once I had the watersheds classified, I extracted information from each of the watersheds in order to look at how much or what percent of each watershed is characterized by each of the land cover classes that I created. So for the Juniper Creek reference watershed that we're looking at right now, you can see that most of the watershed is comprised of forest. But right away, we can notice some errors. So there's not actually any visible water in this watershed. However, there's a very small percentage of the watershed area that's been classified as being covered in water. The reason this is because there were a lot of shadows in the nape imagery, and those dark shadows were classified as water. I had a really difficult time understanding how to reclassify a segmented image. And that is definitely something I hope to learn more about in the future. So unfortunately, I did not perform any reclassification of my classified rasters simply because there were so many tiny little pixels that were classified as water. And I didn't understand how I would be able to go in and select all of those teeny tiny little groups and clusters of pixels in order to reclassify them as their correct land cover type. But you will notice that 10% of this watershed was covered by shadow, at least, probably more than that, which would include some of the water as well. Okay, this is the Juniper Creek Dam watershed broken down into the percentage of land cover type. So 50% or roughly 50% of the Juniper Creek Dam watershed is characterized by forest cover. There's also a significant portion of this watershed that was characterized by grass and pasture, 7% shadows, and as you can see, there's another glaring error in this classification. So this black blob on the screen is actually a small ponded area that got classified as shadow instead of water. I've performed this classification at least a dozen times, and this was pretty much as good as it got. And unfortunately, I was not able to reclassify these rasters in order to get better results. I really did just run out of time. Moving on to Little Pine Knot. For this part, I did separate the watershed, so I extracted the reference area to the reference polygon. Most of this watershed is also characterized by forest. Once again, not any visible water, but there was a small percentage of water that was classified by the tools. And finally, here is the Little Pine Knot Dam watershed. Once again, there is no visible water in this watershed. However, there was a small percentage that was classified as water. However, most of it was classified as forest, which was what I expected to see. And here you're looking at about 8% shadows and about 3% for developed and barren land and 3% for grass and pasture land. Once I had the rasters classified, it was time for me to perform the accuracy assessment. So I needed to start off by creating some accuracy assessment points. There is a tool for this in ArcGIS Pro, so I decided to use it with the help of a video tutorial. My input raster was the classified sites. I named the output accuracy assessment points file. And then I made sure that the target field was the classified raster that I used, and the sampling strategy that I chose was the stratified random sampling strategy, because ArcGIS Pro defines this as the strategy that creates points that are randomly distributed within each class that is used, where each class has a number of points proportional to its relative area. This is also the default standard sampling strategy, so I just chose to go with that one. And these are the accuracy assessment points that were generated for the Little Pine Knot watershed. And these are the accuracy assessment points that were generated for the Juniper Creek watersheds. So this is the table, the attribute table that belonged to the accuracy assessment points that were created by the tool that I just showed you. You'll notice these two fields down here on the end. There's a classified field, which is the actual land cover classification that belongs to each of those random points that came from the classified rasters that I produced. There's another field that's called ground truth. All of the values are auto set at -1, and what you do is individually zoom to each of these points and look at it on the unclassified image and identify what land cover classification that random point belongs to. In order to eliminate bias, I hid the classified field so that I wouldn't have anything swaying what I thought each of these random points belonged to in terms of its land cover categorization, excuse me. And once I identified all 509 points, I turned the classified field back on and scrolled through just to make sure that all of the accuracy assessment points had a classified value and a ground truth value. The last step in the accuracy assessment was to run this tool titled Compute Confusion Matrix. So I created a confusion matrix using my accuracy assessment points, and this was just what I named the confusion matrix table. Once I ran the tool, this is the table that it generated. This table was a little confusing to me, so it took some digging for me to understand what I was looking at. But essentially, these columns across the top correspond to the ground truth classes that were created in the accuracy assessment points. These rows along the side are the mapped or classified classes that correspond to those from my classified rasters. These numbers along the diagonal here are the number of points identified correctly for each of these classes. This is the user accuracy, and this is the producer accuracy. The overall accuracy is down here at the intersection of the user and producer accuracy. So you'll notice my accuracy here was roughly 73%. Because that table was confusing to me, I extracted it as a Microsoft Excel table and opened it up in Excel. So here you can see the Landcover classifications, the numbers of pixels that were identified correctly for each of the classes, and the overall accuracy of my image analysis, which was about 73%. So in conclusion, all 4 of the watersheds that I analyzed contain mostly forest, so I was partially correct in my hypothesis. They also contain lesser amounts of the other land cover types, which were water developed in barren land and grass and pasture. The accuracy of this classification, however, was not sufficient enough for future use of the classified output rasters. I had hoped to find an accuracy greater than 90%, but I only found an accuracy of about 73%, so I wouldn't feel comfortable using these for anything in the future. In the future, what I would like to do is maybe repeat this same project using these same methods, using better imagery that have less shadows. I'd also like more practice with object-based image analysis techniques. I do think that I could get better results if I just did it more often. These are the references that I used to complete this project. I also used the help function in ArcGIS Pro quite a bit. I would also like to take a moment to thank Dr. Keller for all of his efforts in making this project possible. And thank you for your attention.